Next, NASA says its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again.
NASA's twin Voyager probes, which were launched in 1977, awed the world with their grand tour to Jupiter, Saturn, Uranus, and Neptune. Both probes continue their trip into interstellar space 47 years later, providing new insight into some of the big mysteries of our solar system. And in a world-shattering revelation, NASA has announced that Voyager 1 has made an astonishing discovery about interstellar space. This unexpected find defies current scientific understanding and opens up new possibilities for space exploration and our knowledge of the universe. Join us as we dig deep into the details of Voyager 1's extraordinary discovery that has left scientists and researchers puzzled. The Voyagers epitomize 1970s high-tech. Each is about the size and weight of a subcompact automobile. Their computers are weaker than those in today's digital watches. Their analog TV cameras more primitive than the ones that shot Laverne and Shirley. But they made history at every planet they reconnoitered, confirming, as Voyager chief scientist Ed Stone put it, that nature is much more inventive than our imaginations. Jupiter, which looks serene through a telescope, was shown by Voyager to have hundreds of raging hurricanes, a glowing aurora at the North Pole, and 3 thin rings. Saturn's rings, previously countable on the fingers of one hand, turned out to include thousands of ringlets and seemingly braided components that theorists had assumed were impossible. Active volcanoes, formerly found only on Earth, turned up in abundance on Jupiter's satellite Io and, astoundingly, on Neptune's Triton, where nitrogen geysers were observed erupting at 40 degrees above absolute zero on the Kelvin scale. 2 of the solar system's most promising environments for finding alien life, Jupiter's icy moon Europa and Saturn's Enceladus, were unveiled by the Voyager mission. Their cores palpitated and heated by tidal interactions. Europa and Enceladus appear to sustain vast, briny oceans beneath the ice, where living organisms might thrive. Perhaps the most poignant gesture of the Voyager mission was its final parting salute to its place of birth. The portrait of the Sun's family of planets taken in early 1990 included an image of Earth. Carl Sagan, a member of the Voyager imaging team and the captain of the small team that had produced the Golden Record, had proposed this image to the Voyager project in 1981. He eventually called it, appropriately, the pale blue dot. His motivation is expressed in his book of the same name, in which he describes wishing to continue in the tradition begun by the famous Earthrise images of the Apollo program, referring specifically to the one taken from the surface of the moon by Apollo 17. According to Carl Sagan, another picture of the Earth, this one taken from 100,000 times farther away, might help in the continuing process of revealing to ourselves our true circumstance and condition. It had been well understood by the scientists and philosophers of classical antiquity that the Earth was a mere point in a vast encompassing cosmos, but no one had ever seen it as such. Here was our first chance. On August 25, 2012, NASA's Voyager 1 spacecraft was 11 billion miles, or 18 billion kilometers from the Sun, and scientists determined that the venerable spacecraft had crossed the boundary between the Sun's influence and the interstellar medium. And now, still going and still sending back data after 47 years in vast space, Voyager 1 and its twin Voyager 2, which joined it in interstellar space in 2018, continue to conduct groundbreaking science. Both Voyagers are now so far from Earth that a one-way radio signal traveling at the speed of light takes almost 23 hours to reach Voyager 1 and 19 hours to catch up with Voyager 2. Every day they move away by another 3 to 4 light seconds. Their only link to Earth is NASA's Deep Space Network, a trio of tracking complexes spaced around the globe that enables uninterrupted communication with spacecraft as Earth rotates. As the Voyagers recede from us in space and time, their signals are becoming ever fainter. Earth is a noisy place. Radios, televisions, cell phones, everything makes noise, and so it gets harder and harder to hear these tiny whispers from the spacecraft. Faint as they are, those whispers still meet astronomers' expectations of what the Voyagers would find as they entered the interstellar phase of the mission. A big science endeavor that consumed some 10,000 work years, the mission has been described as one of the greatest voyages of exploration ever conducted by our species. However, it almost didn't happen. Planet and use it to accelerate away from the sun. Gary Flandreau then applied that logic and showed that probes launched in the late 1970s and 80s could benefit from a rare geometric lineup of the outer planets, skipping world to world on gravitational arcs. Neptune, at the solar system's ragged edge, was suddenly reachable in a dozen years, rather than 30. But if the chance was missed, another wouldn't arise until the 22nd century. NASA seized on the opportunity, but shrinking budgets made a grand tour of the outer solar system too expensive. So, the mission was downsized to a $250 million visit to Jupiter and Saturn. But researchers held out hope for a Uranus and Neptune detour. Theoretically, if Voyager 1 worked at Jupiter and Saturn, Voyager 2's trajectory could still be tweaked to visit them. With all options open, Voyager 2 launched on August 20, 1977, on a long, slow trek into the unknown. Voyager 1 followed on September 5th on a shorter, quicker route. Both spacecraft bristled with scientific gear: cameras, infrared and ultraviolet spectrometers, sensors to map charged particles, cosmic rays, and plasmas, a photopolarimeter, and a magnetometer. Nuclear-powered, the Voyager crafts were expected to survive for 5 years. But with some luck and power budget managing, they've exceeded that goal tenfold. Now, renowned as a daring, endless trek to the outer planets and beyond, the Voyager mission became iconic over the years in its scope and meaning. More rite of passage than expedition. More mythic than scientific. The extraordinary images of alien worlds never before seen, and the precognitive sense of being there that they evoked, connected laypeople the world over to Voyager's historic pilgrimage into the unknown, with eternity the final port of call. It was not folly to feel that the mission would gift us all a measure of immortality. The fabled golden record of Voyager heightened the fascination. The two Voyagers each carried a phonograph record of images, music, and sounds representative of our planet, including spoken greetings in 55 languages to any intelligent life form that might find them. This was a message from planet Earth vectored into the Milky Way, a hopeful call across space and time to our fellow galactic citizens. It thrilled to think that news of us and our home planet might be retrieved by some extraterrestrial civilization, somewhere and sometime, in the long future of our galaxy. Because of its never-ending journey, its dazzling scientific discoveries in the solar system, and its human-forward countenance, to participants and onlookers alike, Voyager became symbolic of our acute longing to understand our cosmic place and the significance of our own existence. Up to now, thanks to the twins, humankind has spent more than a decade exploring interstellar space. But as giving humans new insight into some of the big mysteries of our solar system, NASA probes stunned the whole world by revealing that interstellar space even weirder than expected. To make sense of shocking findings, it helps to know that the sun isn't a quietly burning ball of light. Our star is a raging nuclear furnace hurtling through the galaxy at about 450,000 miles an hour as it orbits the galactic center. The sun is also rent through with twisted, braided magnetic fields, and as a result, its surface constantly throws off a breeze of electrically charged particles called the solar wind. This gust rushes out in all directions, carrying the sun's magnetic field with it. Eventually, the solar wind smashes into the interstellar medium, the debris from ancient stellar explosions that lurks in the spaces between stars. Like oil and water, the solar wind and the interstellar medium don't perfectly mix, so the solar wind forms a bubble within the interstellar medium called the heliosphere. Based on Voyager data, this bubble extends about 11 billion miles from the sun at its leading edge, surrounding the sun, all 8 planets, and much of the outer objects orbiting our star. Good thing too, the protective heliosphere shields everything inside it, including our fragile DNA, from most of the galaxy's highest energy radiation. Thus, understanding this threshold has implications for our picture of the sun's journey through the galaxy, which in turn can tell us more about the situations of other stars scattered across the cosmos. As Voyager project scientist Ed Stone said, "We are trying to understand the nature of that boundary, where these two winds collide and mix. How do they mix, And how much spillage is there from inside to outside the bubble, and from outside the bubble to inside? Scientists got their first good look at the heliopause on August 25, 2012, when Voyager 1 first entered interstellar space. What they began to see left them scratching their heads. One of the biggest surprises from Voyager's journey was the detection of unexpected magnetic field behavior in interstellar space. Initially, researchers believed that the magnetic fields in interstellar space would differ greatly from those associated with our solar system. However, what the Voyager probes observed was unexpected. The interstellar magnetic fields closely aligned with the Sun's magnetic field, defying initial assumptions. This alignment suggested that the solar magnetic field extends much farther into space than previously thought, challenging the understanding of how solar and interstellar magnetic fields interact. The interplay between these two magnetic environments indicated that the influence of the Sun does not abruptly end at the heliopause, but instead continues to interact with the interstellar medium, creating a more complex and dynamic boundary than scientists had envisioned. Furthermore, the strength of the magnetic fields measured by Voyager also surprised scientists. Instead of weakening significantly as the probes moved away from the solar influence, the interstellar magnetic fields were found to be unexpectedly strong. This revelation prompted a reconsideration of how magnetic fields behave in the interstellar medium, leading to new theories about their generation and structure. One of the key factors behind this surprising behavior is the phenomenon known as magnetic reconnection. In the interstellar medium, regions of varying magnetic field strengths can interact and reconnect, potentially transferring energy and altering the magnetic landscape. The Voyager's data suggests that magnetic reconnection processes might be more prevalent than previously realized, affecting how cosmic rays propagate through space and how the solar wind interacts with the interstellar medium. The implications of these discoveries extend beyond the immediate findings of the Voyager missions. Understanding the magnetic field behavior in interstellar space is crucial for grasping the larger dynamics of the galaxy. The interstellar magnetic field plays a significant role in shaping the structure and evolution of the interstellar medium, influencing star formation and the movement of charged particles. By revealing the complexity and variability of magnetic fields in this uncharted territory, Voyager has provided invaluable insights that will inform future research. In addition, upon crossing into interstellar space, both Voyager probes detected a dramatic increase in cosmic ray density. These highly energetic particles are abundant in the interstellar medium, and their behavior offers clues about the nature of interstellar space. One of the most intriguing aspects is the way cosmic rays vary in density depending on their origin, and whether they're local to the galaxy or have traveled across vast intergalactic distances. This variation in cosmic ray density near the heliopause could help scientists understand how our galaxy is shielded from extragalactic cosmic rays, potentially affecting the conditions for life in different galactic regions. The increased particle density surprised scientists as well. Rather than the relatively sparse environment that many expected, the interstellar medium around the heliopause is denser than previously assumed. This density fluctuation is partly due to the compression of interstellar gas as it encounters the heliopause, which acts like a pressure front against the outward-moving solar wind. This compressed gas hints at the kind of turbulence and interaction that characterizes the interstellar medium, demonstrating that interstellar space is more structured and active than a vast, empty void. Elsewhere, temperature measurements from the Voyager probes also revealed strange results. Scientists expected temperatures to drop as they left the influence of the Sun's solar wind, but Voyager 1 recorded a surprising increase in temperature just beyond the heliopause. This unexpected warmth in interstellar space could be due to turbulence and the dissipation of magnetic energy. Alternatively, it may be the result of a shockwave effect, where the interstellar medium and solar wind create a cosmic shock front that generates heat. This discovery has led scientists to rethink how energy and matter interact at the boundary of the heliopause. The concept of a shock front suggests that the edge of the heliosphere acts like a giant cosmic furnace, where the energy from the Sun's influence dissipates into interstellar space. This region may not just be a passive boundary, but a dynamic interface that continuously transfers energy, affecting conditions far beyond our solar system. Another intriguing aspect of interstellar space uncovered by the Voyager probes is the presence of plasma waves. Plasma, a state of matter consisting of charged particles, is common in space, but behaves differently depending on environmental conditions. The Voyagers detected plasma oscillations in interstellar space, giving scientists valuable clues about the density and movement of particles in the interstellar medium. In 2021, scientists discovered that Voyager 1 had been recording continuous plasma wave data in interstellar space, revealing periodic changes in plasma density far beyond the heliosphere. This phenomenon could be caused by disturbances in the interstellar medium, possibly from shock waves originating from supernovae. These plasma waves hint at the dynamic and sometimes chaotic nature of the interstellar medium, which is constantly shaped by stellar events across the galaxy. One of the most mysterious findings from the Voyager probes is the detection of an anomalous pressure beyond the heliopause. Measurements indicate that the pressure in interstellar space is higher than can be accounted for by known sources such as cosmic rays, magnetic fields, and plasma density. This unexpected force suggests the presence of an unknown factor or energy source in the interstellar medium, which could have profound implications for our understanding of the galaxy's structure and behavior. One hypothesis is that dark matter or some unknown particle might be influencing this region. Although this is purely speculative, the discovery of this anomalous pressure hints at forces or phenomena beyond our current scientific understanding. By measuring and studying this pressure, scientists hope to shed light on what could be a fundamental component of the galaxy, or perhaps even the universe as a whole. The more surprising and abstract findings from the Voyager probes is the idea that interstellar space might have a foamy texture. This concept suggests that the interstellar medium is not homogeneous, but consists of areas of varying density, creating a patchwork of hot and cold, dense and sparse regions. The Voyager's instruments have detected density fluctuations that hint at this foam-like structure, where different regions may have different magnetic and physical properties. This discovery of a textured interstellar medium changes the way scientists think about space on a galactic scale. Rather than a continuous void, interstellar space appears to be a complex landscape shaped by various cosmic forces. This foaminess could influence how stars and planetary systems form, as well as how particles and radiation travel through the galaxy, shaping the interstellar environment in ways we are only beginning to understand. In short, as the Voyager probes continue their journey, their instruments degrade over time, and their power sources will eventually run out. NASA estimates that they will lose contact with Voyager 1 and Voyager 2 by the 2030s. However, the legacy of these missions will persist long after they fall silent. The data they have collected over the past decades provides a foundation for future interstellar exploration, potentially inspiring the next generation of space probes specifically designed to study interstellar space. In the future, NASA and other space agencies may develop probes that can travel even faster and carry more advanced instruments, capable of delving deeper into interstellar space and exploring the interstellar medium in greater detail. These next-generation probes could investigate some of the mysteries uncovered by Voyager, from the unexpected magnetic fields and plasma waves to the anomalous pressure and particle densities. But to explore interstellar space effectively, we need new propulsion technologies that can overcome the immense distances involved. The fastest spacecraft to date, the Parker Solar Probe, will travel at speeds of approximately 430,000 miles per hour, but it would still take over 6,700 years to reach the nearest star system, Proxima Centauri, located just over 4 light-years away. This highlights the necessity for innovative propulsion methods that can significantly reduce travel time and increase the payload capacity of missions. Solar sails are a promising technology that utilizes the pressure of sunlight to propel a spacecraft. By deploying large, reflective sails, a spacecraft can gradually accelerate as it captures photons from the sun. The Planetary Society's light sail missions have demonstrated the viability of this technology in low Earth orbit. Future concepts envision solar sails that could be deployed in deep space, harnessing the sun's energy or even the radiation from stars. One of the most exciting proposals is the Breakthrough Starshot initiative, which aims to develop tiny, lightweight spacecraft called starships, propelled by powerful ground-based lasers. These spacecraft would be equipped with sails and could theoretically achieve speeds of up to 20% the speed of light, allowing them to reach Proxima Centauri in about 20 years. While the technical challenges of this approach are significant, the potential for rapid interstellar exploration is undeniable. Nuclear propulsion systems are another avenue being explored for interstellar missions. Unlike conventional chemical rockets, which burn fuel and produce thrust, nuclear thermal rockets use a nuclear reactor to heat a propellant, such as hydrogen, to create thrust. This method offers much greater efficiency and thrust compared to chemical propulsion. NASA's Project Orion, which began in the 1950s, proposed using nuclear explosions to propel a spacecraft. Although this concept raised significant safety and environmental concerns, modern adaptations of nuclear propulsion are being revisited. NASA's Kilopower project has successfully tested small fission reactors that could power long-duration missions, providing both propulsion and energy for scientific instruments. Another promising nuclear concept is fusion propulsion, which harnesses the energy released from nuclear fusion reactions. Understanding this interaction is crucial for elucidating the heliosphere's structure and dynamics. The solar wind, a stream of charged particles emitted by the sun, plays a significant role in shaping the heliosphere, which acts as a protective bubble around our solar system. By studying how the solar wind behaves at the heliopause, scientists hope to gain insights into the physical processes that govern this boundary region. Another major objective of the mission is to analyze cosmic rays, high-energy particles that travel through space and can originate from various sources, including supernovae and active galactic nuclei. The interstellar probe aims to measure cosmic rays' composition, energy, and intensity, helping researchers understand how these particles propagate through the interstellar medium and their potential impact on space weather and future human exploration. The mission also seeks to map the magnetic fields in the heliosphere and the interstellar medium. Understanding these magnetic fields is essential for deciphering how they influence particle acceleration, cosmic ray propagation, and the overall dynamics of the interstellar environment. By measuring the magnetic fields and their variations, scientists can develop more accurate models of the heliosphere and its interactions with the interstellar medium. To achieve these ambitious goals, the proposed interstellar probe will be equipped with advanced scientific instruments capable of measuring the properties of the solar wind and interstellar particles in real time. These instruments will include particle detectors, magnetometers, and spectrometers, designed to capture a wide range of data about the plasma environment and the particles encountered by the spacecraft. One innovative aspect of the mission is the potential use of gravity assists from the gas giants, such as Jupiter and Saturn. By utilizing these planetary encounters, the spacecraft can significantly increase its speed, allowing it to reach interstellar space in a relatively short time frame. This strategy not only enhances the spacecraft's velocity, but also reduces the amount of fuel required for propulsion, making the mission more feasible and cost-effective. Reaching the heliopause and studying the interstellar medium requires careful planning and execution. The trajectory of the interstellar probe will be meticulously designed to ensure the spacecraft can navigate the complex gravitational influences of the solar system's outer planets. Once beyond the heliosphere, the probe will embark on a journey into the vast, uncharted territories of interstellar space. This mission holds the promise of answering fundamental questions about our universe. As the spacecraft traverses the interstellar medium, it will provide unprecedented data that could reshape our understanding of the cosmos. The knowledge gained from the interstellar probe could illuminate the processes that govern star formation, galaxy evolution, and the dynamics of cosmic structures, offering insights into the nature of our universe and humanity's place within it. Similar to the interstellar probe, the 100-year Starship initiative funded by DARPA also aims to explore the feasibility of human interstellar travel within the next century. This groundbreaking project is not merely about dreaming of distant worlds. It's a comprehensive approach to tackling the multitude of challenges associated with sending humans to another star system. The initiative recognizes that the journey to the stars is fraught with complexities that extend far beyond technological advancements, necessitating a concerted effort to understand the technological, financial, and socio-political hurdles that must be surmounted. At its core, the 100-Year Starship Initiative seeks to synthesize knowledge from various disciplines, bridging gaps between engineering, biology, social sciences, and more. This multidisciplinary research is essential to developing a sustainable approach to interstellar travel. Each field contributes unique insights that inform the design, functionality, and societal implications of potential missions. For instance, engineering plays a crucial role in creating spacecraft capable of withstanding the rigors of long-duration space travel, while biological research is vital for understanding how humans can thrive in environments far removed from Earth. Additionally, social sciences help us grapple with the ethical and psychological challenges that might arise during such missions, including the impact on crew dynamics, governance, and the social structures that may emerge in an off-Earth context. The goals of the 100-Year Starship project are nothing short of monumental. One of its primary objectives is to establish a comprehensive framework for long-duration space missions. This involves not only designing spacecraft that can support human life for extended periods, but also considering the psychological well-being of astronauts who may be isolated from Earth for years, if not decades. Addressing these challenges requires innovative solutions, such as life support systems capable of recycling air and water, food production technologies that can sustain crews over long voyages, and systems that promote mental health and social cohesion among crew members. In tandem with these practical objectives, the initiative also seeks to explore the implications of interstellar colonization. This includes envisioning what life might be like on a distant planet, how to establish self-sustaining communities, and the legal and ethical questions that arise from human expansion into the cosmos. The potential for interstellar colonization opens up profound questions about humanity's role in the universe and the responsibilities that come with venturing beyond our home planet. How should we approach the prospect of encountering extraterrestrial life? What ethical frameworks will guide our interactions with other worlds? Moreover, the 100-Year Starship Initiative is designed to inspire future generations to look beyond Earth and engage with the profound challenges and opportunities presented by interstellar exploration. The long-term vision encompasses not just the technical aspects of space travel, but also the cultural and philosophical shifts that are necessary for humanity to embrace this journey. By fostering a sense of curiosity and ambition, the initiative aims to motivate young people to pursue careers in science, technology, engineering, and mathematics fields, ensuring a continued pipeline of talent capable of advancing interstellar research. In addition, note that one of the critical challenges of interstellar exploration is the need for resources to support long-duration missions. Concepts are being developed to utilize in-situ resources, materials found in space, to reduce the need for resupply missions from Earth. Asteroids are abundant in the solar system and contain valuable resources, such as water, metals, and other materials. Mining asteroids could provide the necessary resources for spacecraft, including propellant, life support systems, and construction materials. Missions like NASA's OSIRIS-REx have already demonstrated the feasibility of capturing samples from asteroids, and future missions could focus on establishing mining operations. By extracting water from asteroids, spacecraft could convert it into hydrogen and oxygen for propulsion or life support, significantly extending their operational range. This approach not only provides essential resources for interstellar missions, but also reduces the burden of launching everything from Earth. In addition to asteroid mining, the Moon and Mars are also seen as potential resource hubs for future interstellar missions. The Moon, with its proximity to Earth, offers an unparalleled opportunity for testing and refining the technologies required for deep space missions. Its surface provides a relatively safe environment for experimentation, making it an ideal site for testing spacecraft systems, life support technologies, and other critical components of interstellar exploration. NASA's Artemis program is at the forefront of this endeavor, aiming to establish a sustainable human presence on the Moon by the end of the decade. This initiative is designed not only to foster scientific research, but also to create a launch pad for future missions to Mars and beyond. One of the key advantages of the Moon is its low gravity, which facilitates the launch of spacecraft. By utilizing lunar resources, such as water ice found in permanently shadowed craters, future missions could produce fuel and life support systems locally, reducing the amount of supplies that must be transported from Earth. This capability could significantly lower the cost and complexity of interstellar missions. Moreover, the Moon's regolith, lunar soil, contains various minerals that could be processed to support infrastructure development, including building habitats and conducting research. On the other hand, Mars presents a different yet equally compelling set of opportunities. Known for its vast array of natural resources, the red planet is rich in water ice, essential minerals, and potential fuels. As we explore Mars, we uncover not only its geological history, but also its potential to support long-term human habitation. The presence of water, in particular, is a game changer. It can be used for drinking, irrigation for growing food, and even converted into hydrogen and oxygen for rocket fuel through electrolysis. This means that missions to Mars could not only sustain human life, but also prepare for journeys further into space. The prospect of developing habitats on Mars is a major focus for space agencies and private companies alike. Creating self-sustaining colonies could provide valuable insights into the challenges of maintaining human life during interstellar travel. These habitats must be equipped with advanced life support systems capable of recycling air, water, and waste, thereby mimicking Earth's ecosystems. This research is crucial as it addresses not only the physiological needs of astronauts, but also the psychological aspects of living in isolation over extended periods, which is essential for successful interstellar missions. And as we embark on the challenges of interstellar exploration, AI will play a crucial role in mission planning, navigation, and data analysis. The vast distances involved mean that communication with spacecraft will face significant delays, making autonomous decision-making essential. AI can help spacecraft navigate through complex environments, analyze data in real time, and optimize their trajectories for energy efficiency. For example, machine learning algorithms could be employed to identify and categorize celestial objects encountered during the journey, providing valuable scientific data without the need for constant human oversight. Furthermore, AI can enhance the design of spacecraft systems, enabling adaptive responses to unforeseen challenges during long-duration missions. This capability will be crucial for ensuring the safety and success of interstellar exploration.
From our perspective, when you look up at the Milky Way, you see all these stars all over the place. So if you're saying flat, like how much height and what are you saying?
This is fucking scary. We live on a little speck that's like turning in one of many galaxies, you know.
Launched in 1977, Voyager 1 has journeyed beyond our solar system, providing invaluable insights into the nature of space, the planets, and the heliosphere. And now, after nearly half a century of groundbreaking exploration, NASA's Voyager 1 has made a shocking discovery that has sent ripples through the scientific community. Recent data transmitted back to Earth reveal an unsettling new energy field that challenges our current understanding of physics and the cosmos. As NASA scientists analyze these findings, they grapple with profound questions about the nature of this mysterious energy and its implications for our models of the universe. This unexpected revelation not only underscores the significance of Voyager 1's mission, but also opens new avenues of inquiry into the complexities of interstellar space, revealing that even after 47 years, the spacecraft continues to reshape our understanding of the universe. Join us in today's episode as we dig deep into Voyager's unimagined trip and its newest disturbing discoveries. In the 1960s, visionary scientists at NASA identified a rare cosmic event that would lay the groundwork for one of humanity's most ambitious space explorations, the Voyager program. These scientists realized that the outer planets of our solar system, Jupiter, Saturn, Uranus, and Neptune, would align in the late 1970s in such a way that, with the right timing, a single spacecraft could use the gravity of each planet to propel itself to the next. This favorable planetary alignment occurs only once every 176 years, presenting NASA with a unique opportunity to visit multiple distant worlds without needing excessive amounts of fuel. Through a technique known as gravitational assist, or a gravity slingshot, the spacecraft could gain additional speed by harnessing the gravitational pull of each planet, allowing it to continue its journey outward with minimal fuel. The concept of gravitational assists was revolutionary. By strategically using each planet's gravitational pull, the spacecraft could accelerate to speeds otherwise unachievable. This method extended the mission's range significantly, allowing a single mission to visit all 4 giant planets without requiring the heavy fuel loads that would typically be necessary. Initially, NASA's ambitious goal was to send 4 spacecraft to explore these outer planets in a mission called the Grand Tour. However, funding challenges led NASA to scale down this vision to 2 spacecraft. Named Voyager 1 and Voyager 2, these twin spacecraft were designed with resilience and scientific capability at their core. Both Voyagers were nearly identical in design, equipped to be humanity's first interstellar messengers. Each carried a high-gain antenna for long-distance communication with Earth, an array of scientific instruments for collecting data on the planets, and a power source that would enable the mission to continue well beyond the outer planets. The designers even included a golden record, a phonograph record containing sounds and images that represented the diversity of life and culture on Earth. From greetings in 55 languages to music and natural sounds, the record was a gesture of goodwill, intended for any extraterrestrial civilizations that might someday encounter the Voyager probes in the distant future. Despite the reduction from the original Grand Tour vision, the goals of the Voyager mission were audacious. The twin spacecraft would aim to explore Jupiter and Saturn, and, if conditions permitted, extend their journey to Uranus and Neptune. Engineers initially designed the spacecraft to last a generous 5 years by the standards of the 1970s. Yet, as time would reveal, these probes would vastly exceed those expectations. The mission's first monumental moment came with Voyager 1's arrival at Jupiter in March 1979, followed closely by Voyager 2's in July 1979. Until then, Jupiter had largely remained a mysterious giant, only seen in faint images from telescopes on Earth. However, the Voyagers sent back stunning, detailed photographs that transformed our understanding of the planet. For the first time, humanity saw Jupiter's swirling atmosphere and storm systems up close, including its iconic Great Red Spot, a colossal storm larger than Earth that has been raging for centuries. The dynamic and turbulent atmosphere revealed by the Voyager images showed swirling clouds, enormous eddies, and lightning storms far beyond what scientists had anticipated. This newfound insight into Jupiter's chaotic atmosphere provided a glimpse of the powerful weather systems on gas giants, an area of study that continues to fascinate scientists today. In addition to the awe-inspiring images of Jupiter itself, the Voyagers made groundbreaking discoveries about the planet's moons. One of the most significant findings was the discovery that Io, one of Jupiter's largest moons, is the most volcanically active body in the solar system. Voyager images revealed Io's surface dotted with active volcanoes, with eruptions so forceful that they ejected sulfur and other materials hundreds of kilometers into space. This discovery was completely unexpected and showcased the extreme geological diversity that exists within our solar system. Another of Jupiter's moons, Europa, also captured scientists' attention. The Voyager probes revealed Europa's icy, smooth surface, prompting speculation that a vast subsurface ocean could lie beneath its frozen crust. This tantalizing possibility has led to a renewed interest in Europa as a potential candidate for harboring life, spurring further missions focused on this enigmatic moon. Following their successful encounters with Jupiter, the Voyager spacecraft continued on to Saturn. Voyager 1 arrived at Saturn in November 1980, with Voyager 2 following in August 1981. As with Jupiter, the close-up views of Saturn changed our understanding of this gas giant and its stunning ring system. From Earth, Saturn's rings appeared as a solid, smooth band. However, Voyager's detailed images revealed that the rings were made up of countless individual particles, each orbiting Saturn at different speeds. These particles ranged in size from tiny dust grains to massive boulders, creating intricate structures and patterns. The Voyagers also discovered gaps within the rings, some of which were caused by tiny moons called shepherd moons that helped shape the rings by gathering particles into specific formations. Titan, Saturn's largest moon, was another significant focus of the mission. Voyager observations confirmed that Titan has a dense atmosphere, primarily composed of nitrogen, with traces of methane and other hydrocarbons. This thick atmosphere obscured the surface from view, but it sparked theories that liquid methane or ethane seas could exist on the moon's surface. This hypothesis was later confirmed by the Cassini mission decades later, but the Voyagers were the first to highlight Titan's unique environment. After completing their exploration of Saturn, the two Voyagers diverged in their trajectories. Voyager 1 was directed on a course out of the plane of the solar system, setting it on a path toward interstellar space. Meanwhile, Voyager 2 was allowed to continue on its grand tour trajectory, visiting Uranus and Neptune, planets that had never been observed up close. Voyager 2's encounter with Uranus in January 1986 revealed an unusual planet with a highly tilted magnetic field that puzzled scientists. This magnetic field, angled almost 60 degrees from Uranus's rotational axis, created complex and unpredictable magnetic interactions. The spacecraft also detected a faint ring system and discovered several new moons orbiting Uranus, deepening our knowledge of this distant ice giant. Voyager 2's last planetary encounter was with Neptune in August 1989. The spacecraft delivered close-up images of Neptune's atmosphere, capturing the Great Dark Spot, a massive storm system similar to Jupiter's Great Red Spot, but smaller in scale. Voyager 2 also discovered that Neptune's largest moon, Triton, was geologically active, with nitrogen geysers erupting from its icy surface. This marked Triton as a unique body within our solar system and underscored the incredible diversity of planetary environments. With the completion of their grand tour, the Voyager twins had surpassed all expectations. But the spacecraft, though far from any planets, continued to send data as they journeyed toward the boundaries of the solar system. As they ventured farther from the sun, the Voyagers entered the heliosphere, a bubble-like region dominated by the solar wind, which is a constant stream of charged particles from the sun. The edge of this heliosphere, known as the heliopause, marks the boundary between the solar system and interstellar space. Understanding this boundary is critical for scientists, as it reveals how our solar system interacts with the rest of the galaxy. In August 2012, Voyager 1 achieved a historic milestone by becoming the first human-made object to cross the heliopause and enter interstellar space. However, confirming that it had left the solar bubble was complex. As Voyager 1 approached the heliopause, it detected a sharp increase in cosmic rays from outside the solar system, along with a decrease in solar wind particles. The data ultimately confirmed its entry into interstellar space, marking humanity's first step beyond our solar neighborhood. Voyager 2 followed in its twins' footsteps and crossed the heliopause on November 5, 2018, joining Voyager 1 as the second spacecraft to enter interstellar space. While Voyager 1's crossing provided the first direct evidence of the heliopause, Voyager 2's entry into interstellar space allowed for a comparative study, as it carried a working plasma instrument that Voyager 1 no longer had. Voyager 2's plasma instrument provided critical measurements of the solar wind's density, temperature, and speed as it decelerated and transformed when crossing into the interstellar medium. These findings revealed that the heliopause is far from a smooth, static boundary. Instead, it is a dynamic, fluctuating region shaped by the sun's activity and the interstellar environment's varying conditions. Unlike previous assumptions, the heliopause changes constantly, responding to solar flares, coronal mass ejections, and interactions with interstellar particles. Voyager 2's measurements showed that solar events directly impact the shape and behavior of the heliopause, emphasizing that it's an ever-shifting boundary influenced by forces both from within and beyond our solar system. One of the major revelations that came from the twin Voyager missions is the discovery that the heliosphere, the bubble-like region surrounding the sun and the solar system, is not symmetric. Voyager 2 crossed the heliopause at a closer distance to the sun than Voyager 1 had, suggesting that external forces are compressing the heliosphere unevenly. Scientists theorize that this compression results from interstellar medium pressure or differences in solar wind conditions, which may fluctuate depending on the direction of the solar wind's outflow. This finding highlights the complexity of the solar system's protective boundary and hints at the interplay of forces between our solar environment and the vast reaches of interstellar space. Prior to the Voyager missions, interstellar space was often regarded as an empty void, a vast nothingness punctuated by distant stars. However, when Voyager 1 ventured beyond the heliopause, it encountered a surprise. Interstellar space was anything but empty. Instead, it detected dense plasma, or ionized gas, with a density around 40 times greater than that found within the heliosphere. This dense plasma likely originates from ancient supernova explosions, whose remnants have dispersed and spread throughout the galaxy over eons. The presence of such dense plasma in what was once thought to be a barren region has profound implications for our understanding of the interstellar medium. It suggests that interstellar space is shaped by remnants of past cosmic events, and that supernovae play a critical role in filling the galaxy with energetic particles and dense plasma. These interactions between solar and interstellar particles are key to understanding the protective role of the heliosphere in shielding our solar system from these ancient cosmic forces. Another groundbreaking discovery made by both Voyager spacecraft involves the magnetic field in interstellar space. Voyager 1's crossing revealed a surprisingly strong and consistent magnetic field, contradicting previous predictions. Scientists had anticipated a weaker and more chaotic field due to the random nature of interstellar conditions. Instead, the consistency of the interstellar magnetic field suggests that it may be organized in a way that interacts systematically with the heliosphere, potentially even shaping it. This strong magnetic field may help reinforce the solar system's natural barrier against cosmic rays, high-energy particles that can affect both human space missions and conditions on planets across the galaxy. The discovery has pushed scientists to revise their models of the interstellar medium, as they seek to understand how such a strong, uniform magnetic field came to exist and what role it plays in the vast space between stars. One of the more surprising findings from Voyager 1 was the detection of a persistent hum in interstellar space. Using its plasma wave instrument, Voyager 1 picked up a low-frequency vibration in the plasma outside the heliopause, which scientists believe is caused by the interactions between solar wind particles and the denser particles of the interstellar medium. This hum is not merely a sound, but a steady wave within the plasma, marking a continuous interaction at the very edge of our sun's influence. By studying this hum, scientists gain invaluable insights into the density and variability of the interstellar medium. This hum signifies that the region outside our solar system is far from tranquil. Instead, it's a dynamic environment with ongoing interactions that can reveal much about how different parts of space interact with one another. Cosmic rays, those high-energy particles originating from events such as supernovae or gamma-ray bursts, have also been a focus of the Voyager missions. These particles are constantly streaming through the galaxy, but the heliosphere acts as a shield, deflecting and reducing the intensity of cosmic rays as they approach the inner solar system. When both Voyagers crossed the heliopause, they recorded a sudden spike in cosmic ray intensity, illustrating the heliosphere's protective effect. This data is essential for future interstellar exploration and for understanding how such particles impact planetary atmospheres and the potential for life on exoplanets. The study of cosmic rays also provides clues about the high-energy processes that created them, contributing to our broader understanding of cosmic forces and their far-reaching impacts. Despite their vast distance from Earth, over 14 billion miles, the Voyager spacecraft continue to send back invaluable data, revealing new details about the unknown territories they are traversing. Each day, the Voyagers provide a fresh glimpse of the interstellar environment, allowing scientists to piece together a more comprehensive picture of this largely uncharted region. Their instruments, though limited by the passage of time, remain active, capturing information about cosmic rays, plasma density, magnetic fields, and the plasma waves of interstellar space. This continuous stream of data helps scientists assess the broader structure and behavior of the heliosphere and its interaction with the galaxy's forces. One of the mission's lasting legacies will be the unprecedented data collected about the interstellar medium, contributing to our knowledge of cosmic rays and plasma interactions. Each new measurement adds to our understanding of the boundary between our solar system and the wider galaxy, gradually illuminating the environment that lies beyond the sun's reach. This has become the core mission objective for both Voyagers, which continue their interstellar journey with instruments designed to capture even the subtlest signals from the surrounding space. As they venture ever deeper into interstellar space, the Voyagers may even graze the outer edges of the hypothetical Oort cloud, a distant reservoir of icy bodies believed to encircle the solar system far beyond Pluto. While the chances of detecting Oort cloud objects are slim due to the Voyager's trajectory and dwindling power, any hint of such objects would provide groundbreaking insights into the structure of the outer solar system. Even without this possibility, the data they gather will continue to refine our models of the interstellar medium, particularly in how it interacts with the sun's influence, and will aid future interstellar missions by offering a clearer picture of the radiation environment awaiting them. The Voyager's journey is far from over, and their data transmission could extend into the early 2030s, adding new chapters to a story that began over 4 decades ago. Their enduring voyage into interstellar space not only illuminates the vast, mysterious space beyond the sun, but also inspires humanity to continue exploring the cosmos. Through these twin spacecraft, we are forging a pathway into the unknown, taking the first steps into a galaxy that, despite our advances, remains filled with mysteries awaiting discovery. But despite their groundbreaking accomplishments, the Voyager spacecraft, Voyager 1 and Voyager 2, now face a myriad of technological challenges as they continue their extraordinary journey through interstellar space. Central to the operational capabilities of these spacecraft are the radioisotope thermoelectric generators, RTGs, which convert heat from the natural radioactive decay of plutonium-238 into electricity. This ingenious design has allowed the Voyagers to operate for decades, sending back invaluable data about our solar system and beyond. However, as time passes, the power output of these RTGs diminishes, leading to a critical situation. The Voyagers are currently functioning on less than half of their original power supply. To address this diminishing resource, NASA has implemented a careful strategy of energy conservation. Gradually, non-essential systems and scientific instruments aboard the spacecraft have been turned off to prolong their operational lives. However, this careful management comes with its own set of limitations, as the power supply is projected to continue declining to a point where the Voyagers will be unable to communicate with Earth within the next decade. When that moment arrives, the Voyager spacecraft will transform into silent emissaries of humanity, continuing their journey through the galaxy without the ability to transmit data back to our planet. This eventuality raises poignant questions about the nature of exploration and communication, highlighting the ephemeral connection between humanity and its creations. Another challenge faced by the Voyager missions is the vast distance separating them from Earth. As these spacecraft venture further from the sun and deeper into interstellar space, the time it takes for their signals to reach Earth becomes increasingly significant. Currently, it takes over 21 hours for a signal from Voyager 1 to traverse the distance back to our planet, and this delay will only continue to grow as the spacecraft move further away. This extended communication time complicates operational management and scientific data retrieval. Moreover, the signals sent from the Voyagers grow increasingly faint, necessitating the use of large antennas and sophisticated decoding technologies to maintain contact. The reliance on complex systems further adds to the challenges of keeping the Voyager missions active and productive. Despite these technological hurdles, the future of the Voyager missions transcends mere scientific discovery. It encompasses a broader contemplation of their lasting legacy and the philosophical questions they evoke about humanity's place in the universe. The success of Voyager 1 and Voyager 2, which continue to relay data from the edge of our solar system, has laid the groundwork for numerous other space missions. Each of these missions aims to build upon the legacy established by the Voyager spacecraft. One notable mission inspired by the Voyagers is the Hubble Space Telescope. Although not an interplanetary mission, Hubble's capability to delve deep into the universe complements the Voyager's exploration of our solar system's boundaries. Launched in 1990, Hubble has provided unprecedented views of distant galaxies, nebulae, and a multitude of cosmic phenomena. The data gathered by the Voyagers likely influenced Hubble's design and mission objectives, reinforcing the importance of exploring further and deeper into space to answer fundamental questions about the universe's origins, structure, and evolution. Hubble's contributions to astronomy are immeasurable. It has played a crucial role in measuring the expansion rate of the universe, leading to the discovery that nearly every galaxy possesses a supermassive black hole at its core. These revelations have fundamentally transformed our understanding of the cosmos and our place within it. The mission embodies the same spirit of exploration that initially drove the Voyager missions, reflecting a deep-seated desire to push the boundaries of human knowledge and uncover the mysteries of the universe. The Cassini-Huygens mission, a collaborative effort between NASA, the European Space Agency, and the Italian Space Agency, serves as another remarkable example of how the Voyager's exploration of the outer planets inspired future endeavors. Voyager 1 and 2 provided humanity's first close-up images of Saturn and its moons, unveiling a complex and dynamic system that demanded further investigation. Launched in 1997, Cassini was specifically tasked with studying Saturn in greater detail. Over its 13-year mission, Cassini orbited Saturn, transmitting detailed images and data about the planet, its rings, and its moons back to Earth. Among Cassini's most significant discoveries was the detection of water ice plumes erupting from the moon Enceladus, suggesting the existence of a subsurface ocean that could potentially harbor life. This groundbreaking finding was a direct extension of the legacy established by the Voyager missions, as Voyager 1 first detected hints of this activity on Enceladus. Furthermore, Cassini's exploration of Titan, Saturn's largest moon, built upon Voyager's initial observations, revealing vast lakes of liquid methane and ethane adorning its surface. The Cassini-Huygens mission epitomizes how the data collected by the Voyagers set the stage for future exploration, allowing subsequent missions like Cassini to delve deeper into specific targets of interest. Another remarkable mission inspired by the Voyager explorations is New Horizons, which was launched in 2006. While the Voyagers captured the first close-up images of the four gas giants, Jupiter, Saturn, Uranus, and Neptune, New Horizons was specifically designed to explore Pluto, the last of the classical 9 planets that had not yet been visited by a spacecraft. On July 14, 2015, New Horizons made its historic flyby of Pluto, returning detailed images and data that revealed a surprisingly complex world, complete with mountains, plains, and potential cryovolcanoes. This mission not only completed the initial reconnaissance of the solar system's major bodies, but also continued the legacy of exploration initiated by the Mariner and Pioneer missions, culminating in the groundbreaking achievements of the Voyager missions. However, the New Horizons mission did not stop with Pluto. Following its primary mission, the spacecraft was directed toward a Kuiper Belt object named Arrokoth, formerly designated 2014 MU-69, which it flew by on January 1, 2019. This encounter provided humanity with its first close-up view of a Kuiper Belt object, further enriching our understanding of the distant, icy regions of our solar system. The New Horizons mission, much like the Voyager missions, exemplifies humanity's relentless quest to explore the farthest reaches of our solar system and beyond. The Juno mission to Jupiter, launched in 2011, was yet another initiative inspired by the Voyager missions, particularly the groundbreaking data provided by Voyager 1's flyby of the gas giant. While Voyager yielded the first detailed images of Jupiter's atmosphere and moons, Juno was meticulously designed to investigate the planet's composition, gravity field, magnetic field, and polar magnetosphere in far greater detail. Juno's mission has led to new insights into Jupiter's structure, revealing a complex interior characterized by a diluted core. Additionally, Juno has uncovered that Jupiter's iconic Great Red Spot is shrinking, and its polar regions are home to clusters of cyclones, discoveries that significantly deepen our understanding of gas giants. These insights not only expand our knowledge of Jupiter, but also inform our understanding of exoplanets, many of which are Jupiter-sized or larger. Similar to Voyager missions, the Parker Solar Probe stand as monumental achievements in humanity's quest to explore and understand the cosmos. While the primary mission of the Parker Solar Probe is to delve into the mysteries of our sun, it is undeniably influenced by the groundbreaking exploration conducted by the Voyager spacecraft in the late 20th century. Launched in 2018, the Parker Solar Probe is specifically engineered to venture closer to the sun than any previous spacecraft, an ambitious endeavor that promises to yield unprecedented insights into the solar corona, the solar wind, and the various phenomena associated with space weather. While the Parker Solar Probe focuses on solar studies, the James Webb Space Telescope, launched in 2021, embodies the spirit of exploration ignited by the Voyager missions in a different manner. James Webb is designed to observe the universe in infrared wavelengths, allowing it to penetrate dust clouds that often obscure astronomical phenomena. This capability extends our observational reach deeper into the universe, enabling scientists to study the formation of stars, galaxies, and planetary systems in ways that were previously unimaginable. One of Webb's primary objectives is to explore the earliest galaxies that formed after the Big Bang, providing insights into the evolution of the universe. Additionally, the telescope is tasked with examining the atmospheres of exoplanets, searching for the chemical signatures that may indicate the presence of life-sustaining conditions. Just like the Voyager missions before it, James Webb represents humanity's relentless drive to push the boundaries of knowledge, seeking answers to questions about the origins of life and the cosmic processes that govern the universe. These missions, Parker Solar Probe and James Webb Space Telescope, demonstrate the power of sustained exploration. The data collected by the Voyager spacecraft laid the groundwork for future missions, inspiring new generations of scientists and engineers to envision ever more ambitious endeavors. As we look forward to upcoming missions, such as the Europa Clipper, it becomes evident that the pioneering spirit embodied by the Voyagers will continue to inspire humanity's journey into the unknown. The legacy of the Voyager missions has not only shaped our current understanding of the solar system, but has also set the stage for the next era of exploration beyond the heliosphere, the region dominated by the solar wind. One of the most exciting prospects on the horizon is the interstellar probe, which aims to explore the interstellar medium directly. Unlike the Voyager missions, which were designed to conduct flybys of planets and eventually exit the solar system, the interstellar probe will have a singular focus: studying the conditions that exist in the vast space between stars. To achieve its goals, the interstellar probe will carry an array of advanced scientific instruments specifically tailored for examining the interstellar medium's density, temperature, and composition. Understanding these properties is essential for unraveling the processes that govern the interstellar environment and its influence on the formation and evolution of planetary systems. Additionally, the mission will investigate the heliosphere itself, a bubble-like region surrounding the solar system created by the solar wind. Insights into how the heliosphere interacts with the interstellar medium could shed light on the behavior of other stellar systems. Another critical objective of the interstellar probe will be to analyze the boundary regions of the heliosphere, including the termination shock and the heliopause. The termination shock is where the solar wind slows dramatically as it encounters the interstellar medium, while the heliopause is the outer boundary where the solar wind meets the interstellar plasma. Understanding these regions will deepen our comprehension of the dynamics of the heliosphere and its protective role against cosmic radiation. Moreover, the interstellar probe is expected to carry instruments capable of studying cosmic dust, magnetic fields, and cosmic rays. By searching for organic molecules, considered the building blocks of life, in the interstellar medium, the mission could offer tantalizing evidence that the ingredients for life are prevalent throughout the galaxy. thereby raising the possibility of life existing on distant exoplanets. Engineering a spacecraft capable of reaching the interstellar medium and operating there for extended periods presents numerous challenges. The interstellar probe will require a highly efficient propulsion system, designed to achieve speeds far beyond those of the Voyager spacecraft. Advanced propulsion technologies such as solar sails or nuclear-powered engines are being explored to enable this mission. Power generation in the cold, dark environment of interstellar space poses another significant challenge. The interstellar probe will likely utilize radioisotope thermoelectric generators, RTGs, similar to those used in previous missions. However, the extended mission duration necessitates the development of RTGs with improved efficiency and longevity. Communication also represents a formidable challenge for the interstellar probe. Sending data back to Earth from the vast distances of interstellar space requires advanced communication systems capable of transmitting signals over long distances with minimal power. Establishing a network of deep space communication stations will be crucial for receiving the faint signals transmitted by the probe. The scientific potential of the interstellar probe is immense. By venturing beyond the heliosphere, the probe could yield our first direct measurements of the interstellar medium, offering profound insights into the conditions that prevail in the space between stars. These measurements could answer fundamental questions about the origins of our solar system and the processes that have shaped its formation over billions of years. The prospect of discovering organic molecules in the interstellar medium is particularly exciting. If found, these molecules could suggest that the essential ingredients for life are distributed throughout the galaxy, raising hopes for the existence of life on other planets. The interstellar probe could also shed light on the structure and dynamics of the heliosphere, helping us understand how our solar system interacts with the interstellar environment. Moreover, the probe could provide critical data about cosmic dust, which plays a significant role in star and planet formation. Analyzing cosmic dust's composition and distribution could reveal insights into the processes that drive the creation of planetary systems. The exploration of cosmic rays, high-energy particles originating from supernovae and other cosmic events, is another fascinating aspect of the interstellar probe's mission. Understanding cosmic rays' origins and their impact on the interstellar environment could enhance our knowledge of the fundamental processes occurring in the galaxy. In summary, the interstellar probe represents a bold step forward in space exploration, challenging the limits of what is achievable while pushing the boundaries of our technology and understanding of the universe. If successful, this mission could pave the way for future endeavors to explore exoplanets and search for signs of life beyond our solar system. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.